This tutorial describes the operation of the device WL430, which is utilized to understand conduction and convection heat transfer phenomena. The corresponding WL430 software is housed on the computer next to the device and will be utilized to obtain the data from the experiment. The objectives of this lab section are to understand conduction and convection heat transfer in extended surfaces or fins, understand and estimate material properties and the convection heat transfer coefficient, study the effect of material properties in geometry on the heat transfer rate, and draw engineering-based comparisons about conduction and convection heat transfer. Conduction heat transfer is the transport of thermal energy within a stationary medium, which can be a solid or a fluid, as a result of a spatial temperature difference. The conduction heat transfer rate is proportional to the material's thermal conductivity, area of heat transfer, and the temperature gradient. Convection heat transfer rate can be defined as the exchange of thermal energy between a solid and a moving fluid that are at different temperatures. The convective heat rate is proportional to the convection heat transfer coefficient, the heat transfer area, and the temperature difference between the solid and the fluid. In general, an extended surface refers to a geometric configuration utilized to enhance the heat transfer between a solid and a fluid. In particular, a fin is a solid of small cross-sectional area protruding from a larger surface into a fluid at a different temperature. The goal of fins is to increase the energy transfer between the solid and the surrounding fluid. In this analysis, heat transfer due to thermal radiation will be neglected. The WL430 is designed to be a tabletop device. In the device, the heated rod acts as a fin. Thermal energy is transported into the base of the fin, conducted through the fin, and dissipated to the environment at its surface. The main components of the device WL430 are the main switch. It powers the instrument and it is located on its rear side. The heater housing contains the heaters and a port for inserting the metal sample, rod, or fin. The fans. 3 fans on either side of the sample allow airflow to be blown over the sample, generating forced convection heat transfer. Honeycomb structure. Located at the fan's outlets, this structure helps create a uniform flow before flowing over the sample. The sample. 7 possible rod samples can be inserted into the heater housing port. The samples are of different length, called long and short, and materials, including aluminum, brass, copper, and steel. Temperature sensors. 5 thermocouples are to be placed inside designated holes in the sample to measure the temperature as a function of the sample's length. Refer to the laboratory guide for specific details about the sample and the location of each thermocouple. In this video, we will describe activities which utilize the device WL430 heat conduction and convection to study heat transfer in fins. Before operating the machine, make sure to wear safety goggles and adhere to laboratory safety rules. Select sample as per guide. Use a very small amount of thermal paste if necessary. Insert it into the heater housing port. Rotate clockwise until an audible click is heard. Use a very small amount of thermal paste if necessary. Insert the thermocouple into the designated holes along the rod. Avoid bending the thermocouples. Ensure the thermocouples are fully inserted into the rod. Use the thumb screws to secure the thermocouples. Thermal paste overflow should not occur. If it does, clean the excess. Turn on the device WL430. Turn on the computer connected to the WL430. Log in using your University of Arizona NetID. Open the WL430 software. Make sure that the option Hide Values is not selected. Go to View, Hide Values, and uncheck if necessary. Select Fan Calibration under the View tab. Click Start to calibrate the fans and wait for the calibration to complete. The calibration ends when the fan stops spinning and the software shows all fan units are checked. Select Test under the View tab to view the operational conditions. Click Tear to zero the thermocouples. Select the proper material and size in the Material drop-down menu. Click on the gear icon to see the sample properties and location of the thermocouples. Take note of the dimensions and properties. Go to Data Logger in Modules and start recording. This must be done when you are ready to start the experiment. By clicking on the Start-Stop icon, the data will start recording in a .tdms file. Write down the file name. You may need it later. At the end of the experiment, save the file as a .txt file. Click on Fan Unit to turn on the fans and select the desired fluid speed. Input the power percentage of heater 1 to initiate experimentation. Data is already being recorded. Click Chart Recorder to view live data collection. Click on Evaluation to see the temperature distribution only. Click on Refresh arrows to update the data presented in the plot. In this window, the temperature gradient at any time and location can be obtained by selecting Yes in Draw Tangent. If necessary, take screenshots when steady state is reached. Before ending the experiment, the data acquisition should be stopped by clicking on the Start-Stop icon. Click on Pause in the Chart Recorder window. Export data .tms files as .txt files and save it for future use. To end the experiment, set heater power to 0% and the fan speed to 0 meters per second. Click on Cooler to turn on the cooler. This helps the system to cool down. Wait for the system to reach room temperature, steady state, before beginning the next experiment. Open the .txt file with Microsoft Excel and save. The data collection portion of the lab is now complete. Verify all data has been saved and begin to properly shut off the machine. Only begin machine shutoff once the sample has cooled to a safe temperature. Close out the software. Turn off the power switch.